Okay, good afternoon, everyone, and welcome to the Construct Innovate webinar series on modern methods of construction. So this is the 8th webinar in the series that we're having, and today the focus is on modern methods of construction applications in schools and commercial buildings. My name is Jamie Goggins, and I'm a Director of Construct Innovate, which is Ireland's National Research Centre for Construction Technology and Innovation. We're hosting this webinar in association with Engineers Ireland, West Region. So we're delighted to have another lineup of fantastic speakers today. So we have Kevin Dolan, who's Head of Design at Vision Build, and he's going to talk about modern methods of construction category 1. So in previous webinars, we've talked about the different categories. So he's going to talk about 3D, volumetric, modular, permanent buildings, and in particular around the innovation and sustainable school building that's going on at Vision Build. Then we have Catriona, Duggan, and Gottstein, who are directors of Gottstein Architects, and they're going to speak about the use of mass timber in commercial projects, such as the Mass Industrial Warehouse project in North Dublin. And then we have Dr. Noel Harrison, who's a principal investigator in Construct Innovate at the University of Galway, and also is a principal investigator in the IFORM SFI Centre, and he's going to talk about robotics and additive manufacturing in construction. So I'm conscious that we have, want to get, listen to the speakers and hear some great insights from those speakers. But if you want to get more insights, don't be afraid to post in the Q&A function. So you'll see the Q&A at the bottom of the page. You can put in the Q&A and ask the questions, and we'll deal with all the questions at the very end of the webinar. So you can post those questions during the webinar series or during the webinar today. And at the end, after the 3 speakers, then we will go through those Q&A. So without further ado, I'm going to hand over to our first speaker, who's Kevin Dolan, Head of Design at Vision Build. So over to you, Kevin.
Good afternoon, everyone. I'll just share my screen and so I'll give you an overview of the category 1 3D volumetric systems that we use in Vision Build, but particularly innovations around sustainable permanent buildings in that. So I'm Head of Design with Vision Build, and we have an extensive team across all functions, project management, operations, installation, manufacturing, health, safety and sustainability, commercial procurement, finance, and central functions such as finance and HR. What I lead up is design, research and development, and I have a supporting function to the quality director of the business. We have a suite of consultants who work with us repeatedly on projects, and this is to do with the standardized approach to our building system across all the disciplines, as you can see there. And that's just a quick infographic of our geographic spread across the country between our manufacturing locations, offices, live projects and completed projects in our supply chain. So Vision Builds deal with all stages of projects. We do pre-contract service agreements. We do the pre-design. We can take it from concept all the way to turnkey handover. Effectively, Vision Build is a design and build main contractor providing turnkey solutions. And in that, we manufacture and assemble the product ourselves. The category that we work in mostly is category 1, 3D volumetric. However, we also provide category 2 and category 5, depending on the sector that we're dealing with, whether it be residential, educational, life science, or healthcare. And we have a suite of certification, as you can see across the bottom of the screen there. This is our facility in Tubbercurry. We have repurposed an existing building. This is quite conscious of our carbon footprint of our operations. And you can see some of the finished modules, volumetric modules, on the factory floor and leaving the premises. So just to give you a little bit of an example of some types of buildings we do, without getting too in-depth on it. For example, this large school building in Dublin is a permanent building built to the full rigors of the building regulations, BCAR, NZEB, but will be relocated. So our buildings are designed to be relocated. That was an on-site installation of 10 weeks. However, most of the work happened, obviously, earlier on in the program, rather than waiting for your construction stage information. So that's one of the key differences in category 1 and category 2, obviously. We have relocated one of our buildings already in a 3-week period. However, that was only a single-story building, so obviously it'll be a longer period for big buildings like this. This building will decant off this site when the permanent building is built. So we like to not talk about our buildings as temporary buildings. They're permanent buildings that will relocate. A bit more information on that. So we had a full fit out, specialist rooms, 100 modules, 2,500 square meters for the Department of Education. So we provide everything except the loose furniture, basically, is the product offering. Here's a commercial building in the UK that we did. It gives a nice simple overview of a multi-use building, welfare and office facilities for a rail client. The key aspect of this project was that it was built extremely close to a live commuter rail line for Network Rail. So it is one of the advantages of this type of category 1 system is that you can have a very low impact on operations on a live campus, be it rail, be it education, be it healthcare. So to get to the sustainable aspect of it, we have a roadmap to reduce the carbon intensity of our product and our operations. And you can see some of the milestones in it there. So a big part of that is life cycle analysis and whole life cycle analysis of the carbon of the product and how it operates. This is the journey we're on. And you can see some key things that we're doing in terms of the primary structure as well will be covered now in a moment. We have a huge drive towards the social value of our projects and our operations. So I won't go too in depth into that on the moment. So the structural embodied carbon assessment, the primary structure of the building is where typically the perception will be that there's the majority of the embodied carbon. But I'll show you now how on this example, we have our heat map of the primary hot rolled steel structural frame. We can see obviously the heavier section sizes are bringing with them a heavier carbon load to the building. We design our buildings to be as efficient as possible in terms of this. The standardization of the components and the module sizes is a big part of that, and repeatability of design, and also sourcing the raw materials from low carbon options. And there are quick wins for everybody in the industry in regard to that, and more supply chain options are coming online in a relatively cost neutral scenario. So it's something that everybody can achieve on their projects. But when we add in all of the rest of the building, the envelope, cladding, fit out, finishes, MEPH, we can see that 230 tons and 140 tons, they're not, neither one is insignificant. And there are gains and betterments to be achieved in both. One of the key aspects of designing buildings to reduce the embodied carbon, obviously, is the weight of the building. Our buildings are typically 25 to 30% lighter than traditional construction. You have an automatic win in the size and extent of the foundations required for that building. And the foundations being concrete, obviously, so there's quite a significant difference there. So how do we get to that point? We design with the circularity and sustainability targets in mind from the inception point of the project. So if we look at this and we see that the EU waste hierarchy on the right and the circular economy diagram on the left, the reusability of these buildings long term over not just their 60-year design life, over multiple lifespans, some aspects of the building will have to be upgraded perhaps for new building regulations 30, 40 years into the future. But the majority of the building has to be reused. That is the future of the built environment. So our buildings being non-destructible, relocatable is very, very advantageous. And you can see how the building will become a carbon asset in the future. And we're already seeing this coming into legislation in the future, in the near future. And there'll be incentives and penalties related to carbon, and this will drive this into real action in the future. And we are one of many early adopters, I would imagine, in actioning this in real life buildings. So some of the acronyms, and our industry is great for creating acronyms that don't necessarily explain themselves. So just one thing on DFMA, design for manufacture and assembly, designing a product so you know that it can, and the building being the product, you know that it can be manufactured, assembled, and then the extra D for disassembly. And you could put an R at the end for reuse possibly. The earlier you can action a change in that design, the less cost it's incurred, the less abortive work that's incurred. So the little graph on the left explains how we have the same amount of information to get through in our projects. We just have to front load the program of the overall project with the decision making, and the critical path being the information release. All of the decisions have to be made early on in the project. When you get to site, it looks very quick, but a lot of work has happened early on in the project. And the reusability of standardized components, sub-assemblies and assemblies means that you don't have to have copy and paste buildings in the built environment to make Category 1 happen. You can still have multiple options in terms of interior fit out and external facade to keep the built environment aesthetically pleasing and interesting and valuable to society. The structure, the skeleton of the building is what's important to standardize. So if we look at this quick, we have a quick tool for very early concept design. If we look at the building that I had on screen a moment ago, and you build it in a traditional sense, theoretically 527,000 tons of embodied carbon for the primary structure, if we just look at that, or for the entire building, sorry. And if I just switch that then to how our system delivers that building, straight away you can see a reduction from the baseline scheme of 30%. So that's a very quick way of assessing the building at early stage before you get into design development and specific product selection, where you have much more options to deal with this. But I suppose my key message to everybody is, if you design a building in early stages for one methodology of construction, you may preclude other systems or other methodologies. But if you design for MMC Category 1, 3D volumetric, it's our opinion that you do not preclude any methodology. You can then go with Category 2, Category 1, or traditional construction. You have not precluded any of these options, and your client, stakeholders, investors have the options to choose based on their own targets and legislative targets that will come up in the future. That's it for me. Thank you.
Brilliant. Thanks, Kevin. That's very insightful presentation. As I said, if anyone has some questions for Kevin, just put them into the Q&A function at the bottom of your screen there, and we'll come and deal with those after all three presentations. So without further ado, I'm going to move on to our next presentations. So we've got Catriona and Ackman, who are going to present around mass timber and commercial projects. So over to you guys.
Thank you very much. So we're here to speak a little bit about logistics project that we're involved in. We're involved in a number of these, and we're here to share how we came to MMC in through a sustainability route rather than probably an MMC objective to begin with. So we'll just speak a little bit about what we mean by logistics buildings, where they're typically located, why as a building archetype we thought they were worthy of greater attention than perhaps they've been getting, and how we generated an approach to change how these buildings could be designed, and when we can see that happening. Just to speak a little bit about our practice, we're a research and design practice. We operate across all of the scales of buildings, from very small buildings to extra large buildings in excess of 10,000 square meters. The common thread throughout all our projects is that we are focused on mass timber construction, and we have, over the past 16 or 17 years since we first became adept at mass timber, have incorporated it across all or multiple building archetypes and scales. So to speak firstly about what a logistics building typically is, so we find them to be large commercial boxes located adjacent to existing motorway infrastructure, tend to be surrounded in impermeable surfaces and quite a defensive architecture, often very little regard given to orientation or the impact that the building might have on the environment around it, and not alone on ecology and placemaking strategies. So typically, this is what we find, typically built in steel portalized structures, highly efficient from a structural point of view, and cold form secondary structures, and typically located within a apron of concrete hard standing. Typically found on the periphery of cities. In Dublin, the area that we're going to share with you today is located adjacent to the M2 motorway, just off the M50. And we became familiar with this statistic a number of years back, that there had been 5 million square feet of logistics space in the planning. And I suppose that put us thinking as to how could this sector perhaps be influenced to a new a way of constructing these buildings in a less impactful manner. So why logistics? So I suppose there's a number of well-documented reasons as to why the logistics sector has become a highly invested sector in recent years. E-commerce and global pandemic, COVID pandemic, both pushed investment from downtown locations to the periphery of cities. So there was a vast growth in the requirement for industrial and logistics buildings around the periphery of the city, and it has had historically low supply and very low vacancy rates, I should say. Then there's been other national factors in the Irish context, such as low taxation and Brexit, and high investment yields that have driven the sector, and very low vacancy rates. So that's why I guess it became a topical building archetype. And so in terms of how do we approach the design of these buildings, we view it at a number of scales. So we view it at city scale, at site scale, at building scale, and at detail scale. And really what we try to create is this integrated approach where our thinking at all of the different scales, our thinking is simultaneous, I suppose, at all of the different scales. And so, we're considering factors such as biodiversity and ecology, sustainable mobility links, climate resilient design, reduction of urban heat island, improvement of social value and community placemaking. And then when we look at the site level, we look at health and well-being and water management and so on. And then when we get to building level, we look at the operational and embodied carbon, circularity, resource use, and then at detail level, the MMC processes and design for disassembly. So in terms of creating a framework within our own practice, we work to the Sustainable Development Goals, and we use a tracker tool which identifies goals and then targets within the goals that our projects can achieve. And so we identify which of the SDGs is applicable to the project, and we track that through those different layers of city, site, building, and detail, and see how, whether it's life on land or climate action, that we always track which of these goals is applicable and what targets can we achieve within those goals. Then, sorry, just to speak about the city level strategy. So this is the site that we are currently constructing. So it consists of 4 logistics buildings adjacent to the M2 on a linear site sandwiched between the Old Ashburn Road and the new motorway network, just off the M50. So we started by generating a city level strategy of how do we respond to the context that we're in. And so we developed strategies for community and social value, where we created a linear parkland along the edge of the site, which contains sustainable mobility, cycle paths, pedestrian areas, connections to bus stops, and provides connections ultimately to the Charlestown Lewis extension. And strategies such as promoting biodiversity and movement of ecology through the site, and reducing the amount of sealed surfaces within the site, and generating a blue infrastructure strategy. So as we get to the site level, as I mentioned, there's the parkland that addresses placemaking. We minimized traffic impacts, so we carefully located the HGV yard areas which screened between buildings to reduce their impact on the environment and the adjacent office spaces. We minimized hard surfaces. We optimized the green infrastructure, optimized water and blue infrastructure, and promoted ecology movement through the site. When we look at it then, when we get to the actual buildings, what we see is again, an optimization of the positioning of office buildings, optimization of daylighting, and positioning of offices in locations where natural ventilation can be used rather than reliance on services, and then where we can create biophilic areas around the offices to create pleasant working environments for the staff, and areas that we can conceal the parking within a parkland area, and create optimized yard areas that are screened and protected from the outside environment, and then use opportunities to include SUDs and blue infrastructure as something that is qualitative to the environment and to the experience of the users, as well as reducing the demand on the drainage system. And then when we look at building level strategy, we set targets for operational carbon and also for embodied carbon. We in terms of embodied carbon, we found it difficult to have comparative data that we could use as a target to design to. So we settled on designing to a 40% carbon reduction. And in order to do that, we effectively created a digital twin designs that would compare different strategies and show what reductions we can achieve on a like-for-like basis. Then we try to optimize on-site renewables, health and indoor environmental quality, and reduce water consumption and increase greywater recycling. Then at detail level, we looked at what low carbon materials could we use in the construction of these buildings, how would that promote reuse and recyclability, and how would we incorporate MMC or DFMA or DFD into our design process to, again, all with a view to reducing the overall environmental impact of the development. So we looked at the building as a series of layers. So we look at it as substructure, superstructure, skin, the space, and the services. We did research as to where the impacts generally lie, and just by way of, at a high level, I suppose we see that in warehousing projects based on UK data, approximately 50% of the embodied carbon is up front in stages A1 to A5, but 75% of the carbon is whole life carbon, and then there's about 25 of it that's operational carbon. So we set about how could we tackle those figures, and we identify that this substructure and superstructure comprise approximately 65% of the overall upfront embodied carbon. And so that's the first area that we tackled. And so we looked at, I suppose, what is business as usual? Are these highly efficient portal steel frames? What might an alternative be? And so we looked at this regenerative approach. And as I said, we created a clone building. So we designed it in a typical steel portal to achieve the most efficient design in steel that we could with optimized GGBS. We got to a structural upfront embodied carbon of 278 per square meter, which doesn't meet either the scores, the REBA, or the LETI targets. We then created an alternative design in glulam, and that achieves a 50% reduction in the structural embodied carbon, bring it to 148, and then a braced frame, which reduces it even further. So I should say that with the portalized frame, we meet the REBA and LETI targets, not the scores targets, whereas with the braced frame, we managed to meet all of the targets. And then we look at it from the whole life carbon perspective, and we see where we are. So we modeled both systems in timber frame and in steel frame, and we modeled all of the finishes and so on, envelope and services and finishes, and we see where we land with that. And so we identify that by changing the primary and secondary superstructure, we can achieve 36% of the savings that we set about to our 40% target. When we look at the whole life carbon, we achieve 25% of the 40% target. So we would have to go beyond the mass timber solution to achieve the full 40%. So, the next areas which we haven't adopted in this project, but will be in other projects, is where the skin has to be tackled to make carbon reductions within it. Just maybe to say briefly as well that we, in coming to this, we did extensive international research and field trips with clients and stakeholders, and we looked at best practice internationally, brought groups to various of those sites to show them that it is realistic and that it is being done in other jurisdictions. And we also looked extensively at the transport carbon, because it's one that often comes up for mass timber, And so we looked at what actually are the what is the carbon impact of the transport, and we quickly identified it's a very low part of the equation, or very not very impactful. So this is a number of months back where we can see the buildings coming out of the ground. This is the second building erected. We can see the mass timber frame. In the meantime, the other remaining two buildings have also been erected. So we're now more advanced than my last photos that I have in the presentation. But we can see the very, I suppose, very different architectural outcome, but also the doability, and just in terms of spans here, where we deliberately have matched steel spans. So we see here these main beams are 34.5 meters. So it's the structural capability of the mass timber is enormous. My slide has stuck with me. Sorry. Then we can see how the joints have been designed for assembly and for disassembly, and sort of, I suppose, the careful detailing that's possible. And so some of these detailing was created for both in terms of disassembly, but also was sculpted in terms of getting daylight into the building to reduce the operational energy in terms of lighting the warehouse spaces. So very finally, just by way of summary, I suppose the learnings we took from it. So I suppose setting targets in terms of the generating carbon modeling of twin buildings. So considering it simultaneously, as the previous speaker also alluded to, considering the structural systems in multiple different methods of construction, and identifying the savings out of that. Engaging stakeholders and design teams and project partners at an early stage, and creating field trips to research the topic and to show what's feasible. And then a market readiness is something that we often came up against, and over the last 2 or 3 years has been demonstrated not to be an issue. And then program efficiencies, as also alluded to by the previous speaker, are critical in evaluating the outcome. Barriers, barriers or perceived barriers. Cost, yes, cost is a barrier, and meaningful value engineering was essential in order for it to happen. Fire safety is something that we often are questioned on, which isn't an issue with correct detailing. Insurance is another one that often comes up, and again, that's something that we have identified with. We've identified insurance specialists that have helped us to deal with any concerns that arise under that topic. Acoustics is something that we comes up, but we found to be not the issue. Buildability, competencies, not the issue. Lack of data and rating systems are issues. So the more people that do this, the more data is out there, and the more normalized it becomes. So sorry, I know I'm rushing. I realize I'm slightly over time. So happy to deal with any questions in the Q&A. Thank you very much.
That's brilliant. Thanks a lot. Plenty of questions coming in there for you guys in the Q&A. I know that they have to catch a train at 5:02, so we may, if you could be answering some of those in the text afterwards, and I can summarize those afterwards as well. So just as well to keep things moving, I'll move on to our last speaker here, which is Dr. Noel Harrison, and he's going to talk about robotics and additive manufacturing construction. So over to you, Noel.
Thanks, Jamie. I hope you can see my screen okay there. So I'm Noel Harrison. I'm a lecturer here in mechanical engineering in the University of Galway, and also a member of Construct Innovate. And my main area is in manufacturing and materials in manufacturing. And I spent the last 15 years or so working in additive manufacturing, mainly on the metal printing, metal 3D printing, and more recently then I've also started some activity in robotics. So I'm going to talk, really about a couple of observations in terms of robotics and additive manufacturing, and some maybe mention some planned work that we're have in this space through Construct Innovate. But I would say, like, overall, really the impressive stuff is what we've been hearing from our company speakers today and right throughout the webinar series, that, these technologies, they're not futuristic. They're here right now. They're in use in Ireland by companies in the construction sector. So you'll see I'll be drawing on some of the previous talks that are that have been given in the webinar at a couple of stages in my presentation. So first thing is, in terms of robotics, first thing to note, if you're not overly familiar with the evolution of the sector, is that, okay, we're all familiar with the different industrial revolutions, but the biggest thing that's happening in the last maybe 15 years or so is the cost of robots has really plummeted. So for a long time, robots were exclusively used in large factories, mainly because those companies typically were the ones that could justify the investment in this type of hardware. But there is a big change happening. We can see, like, a typical market price for a standard spec robot costs about 10% now of what the same spec would have cost about 25 years ago. So robotic tech is now within the reach of all companies, and definitely within the reach of SMEs. And we're seeing that across all manufacturing sectors and in the construction sector. We send our students out in engineering in Galway. We send our students out on placement in their penultimate year, and we've seen a big jump in the last 3 or 4 years of the kind of exposure our students have to robots and advanced automation in those companies, and that's big and small companies alike. So that's largely due to the accessibility and the cost dropping for this equipment. Also, as well as the cost drop in the capability and the spec of these robot technology is increasing. There's hundreds of different classifications of robots available now, and we're not just talking about different axes or different range of motions or the payload capacity or the reach or the range. There's the whole evolution of collaborative robots, the cobots, which are designed for close interaction with a person, so it's not a robot that needs to be locked away in a cage. And we also have the mobile robots as well that are now taking a foothold in automation and in manufacturing, particularly in the construction sector. So that's one big area of interest for us. Overall, the big drivers for companies in the construction space and in the manufacturer space looking towards robots is, first of all, it solves some issues, or helps to solve some issues in terms of labor force, availability of workforce, age profile and demographics of the workforce. So if workforce is getting older, then their ability to perform some manual tasks might be diminishing. There's also a much better understanding of health and safety requirements and protection of the workforce. So if manual tasks can be automated, then that's generally regarded as a safer outcome. I've listed agility there as well. I mean agility there in terms of product design and manufacturing agility, not an individual's agility. And by that I mean with an automated setup, particularly for a multi-purpose infrastructure like robots, the ability to program and to modify a production process due to a different design or a different product range can be quite rapid, as opposed to having to perform retraining of workforce. So that does have some advantages there in that regard. Along with the evolution of robots, the digitalization of everything in manufacturing and in industry is nicely aligned with robotics and automation, because if it's a digital form of our work plant or our products or our processes, then it's much easier to develop digital solutions or linked digital solutions such as robotic control, and to evaluate these, to design and optimize and virtually commission them on PCs or in software before making the physical investment in the plant. There's also the evolution of collaborative and mobile robots, as I mentioned. Again, that's, you might hear the term Industry 5.0. That's accepted by some people as referring to an industrial revolution where the person is put back into a manufacturing site. Okay, so for the previous evolutions, it's kind of like taking the person away, but Industry 5.0 is bringing the user back into close proximity with automated solutions like robots. And we're seeing for certain applications, and this is probably a big one in the construction sector, is the ability to have automation that's mobile and has extra dexterity due to its mobility, its ability for a robot to move around a production site or to move around a production plant site or floor space for offsite construction. Just unleashes new flexibility and new capability, and brings automation for large scale and massive construction projects into a possibility, whereas before we would be limited to planting like 6-axis robots either side of a production line, and now we have robots that are mobile and can move around inside and around and over and under fabricated housing units, for example. So we have a project on the go on that in Construct Innovate. One of the seed projects is called Motor One, where we're working with the local modular housing company to develop a solution for that. One of the other big drivers is reshoring of production, and again, due to the reduced cost of the hardware and the ability to make savings and in terms of transport and in terms of production costs due to these robotic solutions, we're seeing more it becoming a preferred choice for companies to bring production back into Ireland or back into their own countries, whereas before they would have opted for off-site production at lower labour cost locations. Robotic usability, which I mentioned earlier as well, is just the flexibility and the possible solutions that are achievable now with robotic solutions, both in terms of the hardware, the end-of-arm tooling, the software control, and other advances or parallel advances in vision systems and AI are incredibly valuable to driving this evolution forward. And then the obvious one, of course, the eternal striving for quality and reproducibility is greater enabled with automated solutions, as I think is well understood. So a couple of the examples that we see robotics in use in construction include, for example, establishment of metal structures or steel structures for reinforcement of poured concrete constructs. Doesn't necessarily have to be a curved wall like we can see here, but some manual tasks could be automated in that way, and I'm aware of 1 or 2 companies in Ireland looking at that. Other things such as on-site demolition work or finishing operations, as you can see here. There's other robotic solutions for block laying, for plastering, for different things like that. I don't have images of them here, but we do know that there's test cases of that happening here. For the offsite construction end of things as well, we do know that particularly in the modular housing sector, as I mentioned, that's a big driver for automation and production that can exist on production lines, as we can see in the first image here in the top left, is a good example of our standard ability for automation. But when you go to fabricating the 2D and the 3D structures, which we've seen in the previous talks, we do require greater mobility of our robots. So a good example of that would be the image on the left here, where we have a mobile robot. So that's a 6-axis robot sitting on a mobile platform. It gives the ability to move in and around a unit as it's being constructed, as well as performing other operations. So automated robots can be used for equipment maintenance, for part inspection, and basically take advantage of any possible application in modular construction applications. So if any company is interested in looking at robotic solutions, it is, as I said, an active area for the Construct Innovate research program. So do get in touch with any of us if you do wish to evaluate or to develop some robotic solutions for your applications. So just quickly moving on then to the additive manufacturing side of things. So I've borrowed a couple of slides here, as I said, from earlier speakers. So additive manufacturing, it does have its own category within the MMC range there. It's category number 4, as was described by Daniel a couple of weeks ago from UCD. And on that same day, we heard from Paul Tierney, the head of MMC Ireland, who gave us an overview of the activity or the landscape in Ireland for activity, and we can see straight off that the category 4 is, it looks like it's the lowest activity in terms of number of companies and number of members at it, but it is certainly a very active space. And we heard again from a couple of, was it 2 weeks ago, Andre from Hardcore Technologies gave a talk as well, explaining what they're doing in terms of driving and leading concrete construction in Ireland. So one general observation I would make on that is that the fact that it appears to be a low at the moment is at the bottom of a curve, I would say, in terms of uptake and applications. I'd say I saw the exact same thing about 20 years ago in the metal additive manufacturing space. So that was a technology that started to be developed in the early 2000s. And the main applications for that were in the medical device space and the aerospace sectors. And both of those sectors, which on their own are two, very highly regulated sectors, they were able to push through the acceptance, and what comes with that is the standardization, the regulation, the requirements, and the confidence in reproducibility and quality and so on. They were able to do that for metal printing in those highly regulated sectors, mainly because it was clear that there were some very worthwhile capability achievable through metal printing, and specifically the design freedoms that metal printing gave those industries were worth the effort and the overhaul of those sectors and the disruption of those sectors to push through a new manufacturing method of printing in metal. And that had plenty of problems at the start in terms of porosity and heterogeneity and anisotropy in the printed structures as well. So we're kind of seeing the same thing happening now in the concrete side of things. So I'd be very confident that we can overcome those given the performance benefits and the advantages that 3D printing does give the sector. So I'm not going to explain the process there. You can look back at the presentation, the webinar given by Andre 2 weeks ago from Hardcore Technologies, where they showed a 2-story house that they built on their test site in Drogheda, and he also mentioned other projects that they have on the go, printed housing projects on the go in Sligo and in Donegal. So that's well worth a watch back. Other things to see what's happening, across the world in terms of concrete printing. A couple of the main trends include, first of all, printing at scale. There's one big structure over 900 square meters of a single structure that's been printed in Florida last year. That's, the size scale of the projects that have been printed in Sligo and Donegal are comparable. Okay, they're spread over different units, but the overall projects will be similar footprint or similar floor space. Other applications doesn't necessarily have to mean printing housing. There's printing bridges and printing staircases and other infrastructure. And again, there's some good examples of that available not too far from here, just over in Glasgow. One of the big drivers, as I mentioned, for some of the MMC methods is sustainability, and it's the same thing in 3D concrete printing. You will have heard from Andre when he was speaking on HTLs that they print with concrete. A lot of the technologies that are out there worldwide print with mortar. Mortar is a nicer material to print with. It's more consistent, and it's gives a nicer surface finish and so on, but it's just unsustainable printing at large volumes. So there's a lot of activity that's looking at adding in materials that reduce the overall carbon footprint, and looking at secondary materials and aggregates. There's some work happening from colleagues, Kieran McNally in UCD, that's looking at this, and other ongoing activity looking at waste and applying recovered materials as aggregates, again, as an alternative to reducing the overall carbon footprint of concrete in general. Part of that is identifying processes and controlled processes that we can use locally sourced aggregates to mix into the concrete blend, again, to reduce transport costs and overall carbon emissions. Part of that is one of the things we do want to keep an eye on is what happens, making sure that we're developing and making materials that are suitable for that don't pose problems at their end of life application. So we're not going to combine materials together that they themselves are quite difficult to handle and to manage after the end of life of those products. So a couple of other interesting things are, the 3D printing side of things does allow for enhanced design, and that is one of the big things, as I said, that enabled the uptake and that drove the uptake in the orthopedic medtech space and in the aerospace applications. It was just you were able to make things that you just were not able to make using the existing processes. So there's applications, again, you would have heard from a colleague, Owen King, who's an acoustics engineer, who was explaining that, with fabric construction technology such as concrete printing, you could print non-planar surfaces, and that will allow for enhanced acoustics and move away from these kind of flat planar walls with poor acoustics and poor performances. We don't need it in every building, but for applications, maybe in teaching environments, concert halls, or public buildings, or even outdoor spaces, there's some applications of that taking place. And one other technology that is often mentioned in associated with 3D printing is topology optimization. And again, we can see applications of optimizing the design, reducing the overall material usage costs or usage volume and usage cost, lightweighting structures where possible and only using material where we need it. That particular structure there in the diagram, that wasn't printed, it was cast, but the concept of using topology optimization to define and to produce an optimized structure and reduce the material where it's not needed is directly, runs hand in hand with additive manufacturing technology. So there's lots of applications there. Other trends that we are observing is, further digitalization of the whole thing. We do we're working with companies like Harcourt to see what we can do to enhance our sensorization, to improve our control of the printing process, and to account for changes in temperature or humidity during the day and the sensitivity that any production process or concrete printing process might have to those kind of changes. We're also interested certainly from an engineering perspective and a mechanical perspective, just the whole mechanics of material extrusion, how we can improve the surface finish of the concrete bead, modify the scraper and the nozzle to give us better surface finishes, and to enhance the density and to allow us better to print curved structures or to take bends or to make loops out of our printing process. And we can do that by looking closer at what's happening to the material, controlling the flow, controlling the shape of the nozzle and so on during the printing process. There's other elements related to the concrete rheology and the flow of the material that we might allow us to push the boundary a little bit in terms of the layer height and to enhance our interlayer bonding in the printing process. And that'll be partly related to the modifying other process parameters such as the print speed and the pressure during the pumping stage. Overall, the objective there will be to further increase the process speed, and that's a combined effort in terms of material enhancements and process enhancements. Other things that's happening in parallel are training that's available. Again, there's companies like FutureCast that'll provide training courses in construction and printing in Ireland. They have a site up in Manorhamilton. And there's also activity in Ireland happening. Well, it's happening worldwide, but there's opportunities for getting involved in the emergence of standards, industry standards for construction technology. So one of those has come out last year, additive manufacturing for construction qualification principles. And again, there's lots of activity through the NSAI, which we heard from a few weeks ago as well. So that's, hopefully I haven't ran too much over time there. That's it, basically. That's my observations. If you have any questions, I guess we can take those.